All right, welcome back to the late morning session, I guess. Our first speaker is Sedat Khalil, with lots of affiliations from Lee to Dubai, and he will talk about resident agreements and other kind.
Thank you. Thank you. All right. Thank the organizers for this opportunity. I'm very happy to be here today. And so the whole object of the talk today is it started out as a way to compute error characteristics. This might sound strange, but I think I can try to explain that there are many quick ways to do that using a suitable formalism, and also explain certain other phenomena. So this is the plan. I'll start the first part is explaining some kind of a construction and theory, and then the applications. And I want to get to the applications eventually. So the most basic invariant in topology, obviously, and a triangulation. When you compute the other characteristic on triangulation, that's a stratification. So there's no union of spaces. But when you want to compute this key, you cannot take naively key of x as the sum of the key of x. It would be wonderful. But basically, this is what I want to do eventually. Okay, so this issue is resolved if you work with other characteristic with compact supports. So what is that? Homology with compact supports is divided, as is shown, with their framework of compact set exhausting your space. It's a very beautiful construction, and for finite type spaces, you can take the alternating sum, and that's the other characteristic with compact supports. Sometimes it coincides with K of x, sometimes it doesn't. It does, of course, when spaces are compact. And this other characteristic is called combinatorial sometimes because it has a beautiful additivity. So I want to introduce a topological property which I'll be using all over the place. It has become so essential, and I never expected it to be this essential, local compactness. So space, so we're working in Rn, so everything is nice and house. So locally compact or locally closed are the same things. And the space is locally compact if it's open is closure. We'll write LC in this block. Here's a space that's not locally compact. So it's this triangle together with 2 points. So that messes up various things. So if X is compact, this cohomology of compact support is the same as the cohomology we use. And the key C is the key we use also. Otherwise, if you're in a locally compact Hausdorff, one way to compute is to take the cohomology of one-point compactification whose existence is unique, modulo the point at infinity. Just if you wonder how you want to compute this. Okay. So certifications are decomposition of a space into disjunctional spaces, and for me, all the subspaces in the decomposition are going to be local compact. Depending on which field you're in, you might add some more to certification, like frontier conditions or things like that. All I want is a disjoint union of locally compact or locally closed subsets. And the additivity theorem for other characteristic with compact supports is the one I have on the board, which tells you that if you split a space into, if the space that you start with the locally compact. So if you start with the locally compact spaces, which is itself stratified, decomposed into disjoint union of xi's, all the xi's are locally compact, then the other characteristic with a compact support is added. Okay, so right now, I mean, this is basically the motivation is you make the link between this that shows up over later and key. So you can, using certification to compute the key C and then relate it to key. So it's very useful to compute. A few years ago, some very characteristic of spaces called Barry centers related nonlinear analysis. And that was actually the start of this work. So the ease of this beautiful characteristic. Now, comes something that I was not aware of, shocking. So if X is not SC, is the additive of the third structure? Obviously, the answer is going to be no. Otherwise, no objective to the talk. So the answer is no, and one should be a little careful. So look at the space I have, all right, which is this triangle with these 2 points. It's a full triangle, and you remove this. Right. So the part of the boundary that is in the complement is not closed. To be locally compact, part of the boundary that is in the complement should be closed. That's not the case. And this space is stratified in a nice way. You have the 2 points. Then you have the full triangle minus the edge. The full triangle is closed. The edge is closed. 2 points are closed. So all the spaces are locally compact. And then you compute the sum. And the sum here, and you find that it's 2. And what are we saying? But if you compute that very characteristic of the space with compact support with the formula, you get 0. So they're not the same. Okay, so at that point, we wonder about something. So start with the space that is stratifiable. So it's a disjoint union of locally compact subset, and look at this quantity, which is a sum. What is that? Okay, it would be an Euler characteristic with compact support if the space is locally compact. But for general spaces, where is it?
Does it depend on the certification?
Yes, exactly. So we're getting exactly to it in a second. So definitely we want a construction that doesn't depend on certification. That's exactly. So this thing behaves like an algebra. So if you take, as an algebra homomorphism, so if you take disjoint union of spaces which are themselves disjoint unions, right? So you get a stratification of disjoint union, and then you see that if you take this formula, provided it's well defined, this is that, and it also works well for that part. So it is giving you some sort of an algebra morphism, but where from? All right, so we need to construct a suitable ring here, a stratifiable subspace of Euclidean space, so that this becomes a well-defined non-trivial ring morphism. Okay. Well-defined depending on the stratification. So I want to construct this up.
So well-defined means that it doesn't depend on.
Exactly, that's exactly what it means. And we wanted to coincide with key on compact. So we wanted to give something that we. So this would be done, and the application that we need. Okay, so. Sorry, if I go too fast, let me know. I'm not sure how it is here. The construction is called the Grothendieck-Mean construction, and you are familiar with. So you take the category L of all subspaces that are stratifiable by locally compact. Okay, so this category into continuous maps. I don't really care about maps. So X is in L, it's the disjoint union of such spaces. This is one of them. Okay, so once you have a category, small means that the morphism form a set, so you can look at the set of isomorphism classes of objects. Because after isomorphism, you know, it's okay. It's the same. So I'm looking at spaces that are stratifiable by locally compact sets. You take X and you cut it into strata. This turns out to be something, no. So if you take something called constructible sets, a set union of locally closed subspaces, they could overlap. Constructible set is what is defined over. Then you show that the spaces are defined, which are locally stratifiable, locally compact stratifiable sets, are the same as the constructible sets. And the proof of this is just to show you that this kind of expressions is kind of pretty annoying, but very important in the proof of the main theorem. The proof is not included. But you have to do this sort of theoretic juggling to show that something is constructible if it's locally stratifiable or locally compact sets. Okay, so I have this collection of spaces that are stratifiable by locally compact set, or this collection of constructible sets, and I can define its coordinates. So the Grothendieck ring is a formal definition, which is defined to be the community ring generated by the isomorphism of objects. Okay. Here the isomorphism are homeomorphic, all right? Homeomorphisms subject to these relations. All right. So so here x minus y is in the space if y is in the subspace of x, the Boolean algebra, in fact. And so you want that, you want the relations in this. So you're modding out by the subject generated by this minus that minus that. That's what it means. Or other words, you have this community ring generated by this and subject to these two relations. So this gives you a product, and it is okay. I've seen this before. It's a wonderful little construction. Okay, so we have a ring, and things seems to be great, right? I mean, I have now a ring of strata. I can add strata, subtract strata, and multiply strata. That was a point. Okay, but this ring is 0. So, yeah, I mean, we wrote 10 pages before we realized. Okay, so there are too many spaces. There are spaces that are homomorphic to themselves minus 1. So, so in a ring where 1 equals 0, there's only one. So we have to do something else. And doing that something else is really, I think, the beauty of this. Okay, you get around this is to consider finite type spaces. So definitely this is what you want to do. If you want to make sense of, you know, the bracket, which is called the multivariate morphism. So the bracket, which is the sum of the key C of xi. So the key C of xi should be defined. So definitely you want to be looking at the finite type space. So what's a finite type space? Finite type space is space which whose cohomology with compact support is vanishes beyond a certain degree and finite. There's a lot of beautiful work done in the 60s and 70s. We had to find out about, you know, when this is happening, how there's some sales. So I'll skip that. I'll just show you that you discover some interesting things. So the first condition, Verdi, I think, shows that if you take a space, what we want anyway, locally homomorphic to an open subspace of geometric simulation complex, then this first condition holds. And for compact X, if the first condition holds, the second holds by Billman Wilder. And you have pathological spaces, pretty interesting. You have a compact, so locally compact subspace in R3. So that at Miller, I don't know if you remember that generation. It has cohomology non-vanishing in many. The analog of the polar circle is right. The polar circle is like when you have various circles at one point, and this is you take. This was a question of Steenrod asked Milner when he was a student. And I think Barat and Mendel seem to be of the same age or same generation, and they were both students and they worked it out. So I think Steenrod asked them, okay, instead of taking a bunch of circles, getting smaller and smaller, the polar circle? No, that's the name, I forgot. Hawaiian rings. So then you take the spheres. Take spheres doing the same thing. And then they realized that singular cohomology would not vanish. So this sort of spaces I have to avoid that. Okay. So let N be the subcategory of all subspaces which can be locally compact, stratified by locally compact subsets. But I asked also the finite, so LCFT. Now they are all LCFT. Is it any better? Well, not so. I mean, the complementation is not always there. Okay, so I want to introduce something called we call Lego collections. So the idea is very simple. I already mentioned it in disguise. I want to take a space. I want to take a space and decompose it, stratify, decompose it into subspaces, and those subspaces have some properties. Locally compact, locally finite type, things like that. So I want to make sense of that. It's called a Lego, like a Lego game. So a Lego collection is any subcollection of U, which is made out of a space and the stratification on it. So, so again, these spaces are stratifiable, not stratified. And we had to deal with this. It's not even clear you get the optimal language, but I'm not giving a particular stratification when I give you a space. I'm just saying X has such a stratification. We call it stratifiable. And of course, if you have a space which has a stratification, if you remove a strata, the new space is still in your category. And if you take a product of strata, you get a product of spaces that still is in your category. So, or your collection. Okay, so that's the game. Okay, so is okay. What's the point? Try to avoid writing lots of symbolism. A Lego collection is a family of spaces that can be decomposed into locally compact strata. That's always something that I need. That might have additional properties. So here's are some examples. You'll find many examples, you know, and some that came up in the previous talks. So the LCFT stratifiable spaces, but I threw in finite type on the strata. Sub-stratifiable spaces, CW complexes, subplicial complexes. The strata are the simplices. So these form a Lego category. But the complement of two cells is not necessarily a cell. All right. There is a category of self-stratifiable spaces, such that the complement of two spaces is again in that space. And I discovered that to be all minimal structures, which you have mentioned earlier, like semi-algebraic sets. So the all minimal structures turned out to be a special case of the Lego category. So what they are this construction without throwing in all the compatibilities and conditions. You know, you start an R and build up your family of spaces in Rn for any n through projections, and unions, and complements. And the main theory of the main theorem of the theory is what's called the cell decomposition theorem, which states that any definable segments, any set in this family, can be partitioned into cells. This was it's very useful, and it's a Boolean algebra.
G. Fountain trees. Not fountain trees.
Fountain trees. Yeah, I'm sorry. Okay. Thank you. That should not. So there are these Lego categories where you can assemble things by string. Okay. Now I changed a little bit my definition of the arithmetic ring by saying that if I have a Lego category, so if I have stratifiable spaces, I have this property every time I remove a struct. Not if I have y into x, I don't maybe necessarily have this property because I don't know if x minus y is in my space. But if I have y a stratum of x, if I remove it, I'm left with other stratum. So I changed a little bit my definition of K0, and I get this. So if you have spaces stratified by cells, this K0 is Z, right? Just because you start with R, I mean, this is the trick people in algebraic geometry love to do, but it has this consequence. So if, for example, you start with R, and you see that the class of R is minus, which is, of course, exactly the early characteristic of compaction. So you write R as -0, the positives. You write it this way, you know that R is -1, and R to the n is, of course, because it's a ring, it's -1 to the power n, and so everything is generated by the class of the form. Okay, so something non-zero. Okay. Now, to get back to the question of, probably that's for your name, but your question about when is this thing well defined? So we don't have now a bracket. We don't have. Okay, brackets are like this. That's the Grothendieck ring, right? But I don't have brace, right? That's the class I want to define. It turns out that it's not going to be defined on the cells. It's going to be defined on something like this. So this is the last thing I introduced, the last Lego category I introduced. This is my Lego category, which is M, we called it. So these are all subspaces in M, they're locally compact, yes, and stratified. And now what I want is that the unit of the closures of the strata are finite. Okay. To make things work, this is a small thing we found, but it's not much. Sorry, this is cohomological finite. That's what it is. Which is finite type for cohomological compaction. So not only the xi's are of finite type, but also the closures. So if you, for all applications, this is very easy to have. It's not a big deal, but on this Lego category, okay, so here's the organigram. So we started with all locally compactly stratified ones, then all locally compact finite type ones, then the ones that are stratified by cells. Then you have the what are those minimal structures, and this is the one I'm now looking at. And on this you have this result. Okay, so we do have a beautiful morphism, non-trivial, well-defined and non-trivial morphism into Z. We did define a motivic morphism from this category, from this Grothendieck ring to Z. And this is what I'm going to use in application. Okay. Okay, any questions?
The question is that you gave an example, which is the co-minimal structure.
Right.
But could you bring another example that it is not co-minimal, that satisfies your Lego?
Well, I just gave all this. I gave many that are not even Boolean.
No, but so that you need it to be Boolean.
No, I don't. I don't need to be Boolean. This is why I changed my definition of K0. K0, I said, take X with the stratification, then X minus the stratum is the sum of that. So it has to be a stratum, it's okay, but not arbitrarily any substance. So getting around this problem. Okay. So the applications. I mean, what I'm trying to illustrate is that this formalism gives you such an easy way to compute things. We have various applications. We're going to give you 3 or 4. You see how easy you can work with this. Even computing key, not just key C, but even other characteristics. Right, so the configuration space that showed up in the work at the end, very well known, obviously, the formula that I've shown here. That if you take the configuration space on any X, then this growth entity class is this product. And generally, this is done using Będlewo kind of business. We don't even talk about vibrations here. You just write a two-line stratification. You just stratify your space this way, and you sum. It's really literally 4 lines. So I just included 2 proofs just to show you that how things go very easy if you choose the right stratification to compute. So you take this subspace where x0 is xi for some I, and then you write this to be this. If you think about it carefully, this is simple. And then you apply your bracket. And this decomposition was suggested by Arabia Alberto. I'm not asking you to follow the details, but just telling you that it's a 3-line proof. But this here, beautifully, you'll see it came up with a chromatic polynomial, something very nice, something like that. So then if you take the unordered ones, you get that because you divide by n factorial, and you prove that everything works well for bundles and for coverings. Okay, so you get those 2 classes. You get the other characteristics this way, and that's a proof. That's it. So how do you get key from the growth entity class? You apply your motivic morphism because it's well defined. Okay, so you apply your motivic morphism. It's morphism into Z. So you replace the previous formula. You replace bracket by this brace, right? So you have this, but now you have to know that when X is a manifold, X is this guy, is -1 to the other. So when X is a manifold, this is a manifold. So this is -1 to that power, and X is -1 to that power. And that's it. You replace here and here, you get this form. There's 2 lines. You get this, which is not published. I was surprised. I worked on the subset spaces a while ago. And it's 2 lines. Right. So you take the subset space. It's different than the symmetric part. So sub n of x is the space of all subsets, finite subsets of x, cardinality less or equal to n. The space that shows up. People working on this infinity algebra, moving. So if you want to compute, well, here's a formula. Why? Because if you take the subsets of cardinality n or less, or cardinality n minus union the configuration space, and you sum. As simple as that. And in literature, they have it for bouquet of circles, but they don't have a formula. Generally, it's the symmetric product. I want to just say McDonald's formula is also another 2-line proof, but even more general. People probably know the McDonald's formula is a symmetric product. Okay, so this is all classical. Less classical is maybe graph configuration space. I want to talk about this and also about orbit configuration spaces related to the work of that. So I don't know if you've seen this construction, which I really like, which is the configuration space, the graph configuration space. So what is that? If you have a graph, so you have a certain number of vertices and a certain number of edges, you take the tuples of x1 up to xn, n is the number of vertices, as many entries as vertices, and you say xi is not equal to xj if ij is an edge. So for example, if your space is, if the graph is complete, you get the configuration space. Okay. Let's AK gamma be the number of colonies of gamma by k hubs. So, so you know what the coloring of a graph is. You put a color every vertices and two vertices that are related by that have different colors. Then when you see the chromatic polynomials like this, when you see it like this, immediately you think it should be related to the configuration space. So we had this proof, we were not aware it was already published, of this theorem, but completely different proof. So that the Rothendy class of the configuration space is a chromatic polynomial, where the variable is. It's just, you can say, well, okay, I mean, what can you see? You see that you can stratify your space. You can stratify your space by configuration spaces. Exactly, the colors gives you which configuration spaces you use. This is yeah, I mean, that's this result. And then you get the key from it, which I'm not aware of it published anywhere, but you get it also by applying your motif morphism immediately. I just wanted to show you a proof, but I won't have time because I want to show you the other example. But this is just you stratify by configuration spaces, and with some you get exactly the chromatic polynomial. Oh, I added this morning. Sorry. Okay, I just noticed that I was reading that as a graduate student, Drew Hall, who just won the Fields Medal, proved two things that I knew, but I didn't know that he proved them, which is that the chromatic polynomial is unimodal and log concave. It's just sorry, just a throwing in this. It's one of the things he proved. So this is the chromatic polynomial of this graph. Okay, it's cut. Sorry, it's hexagon, and you see that the coefficient increase decrease, and that's going to be always the case. All right, and the last one is the orbit configuration spaces. I'm going to go through this quickly, and this is the one that came up also in the work done where you take and so if you have finite group acting on space X, you take all points that lie in different orbits. Exactly what it is. It was defined by Miguel Pentacle, who was a student at Co. And if the action is triggered, you recover configuration X. And the Euler characteristic of this is not known, as far as I know. And all I wanted to do, I mean, the formula is at the end, but all I wanted to tell you is that if you have, the interesting thing is that in order to compute these things, you won't come up with a stratification. And it turns out that if you have any group acting on space, it's going to give you an LCFT stratification for free. It's called the orbit type stratification. Very, very useful stratification, actually. This theorem, if G is finite group acting parameterizable X space, then these spaces, the fixed points, and these XH, they have a name I forgot, which are all the X's whose isotropy is conjugate to H. But these give you strata of your space. So a group action stratifies your space. This is exactly what you need in order to solve this problem. This is for example, if you take S3 acting on the triangle, this is the stratification gives you. You take S3, a little group, or and the group of isomorphism. So if you want to work this exercise, and since I have to leave, we get a formula because you can completely you get the Rothendy class, but if you work with a manifold, you can replace this with -1 to some power to get the Euler characteristic. Thank you so much.
Knows very well.
Sorry?
That this graph configuration space and taking Euler characteristic is kind of one of examples of Chobanov type categorification. Probably know because it has the paper. And it is done in paper by Baranowski and Sastanovich.
I didn't know about this paper. I would love to see it. I know the paper by Hackett and
And the Ask
Eastwood.
conjecture and the South by Baranowski and
Okay.
yeah, so
thank
yes, it was just comment that this graph configuration is related to Hopper.
you. Interesting. Thank you. What was the question then?
You needed a finite group.
I think for the
Stratification.
I always work with a finite group. I don't know if the proof goes through, but the Lie group would be fine. I think. Yeah.
Okay, let's thanks for again.
Thank you.
Awesome.